expert level talk by Sonja Hohloch, and you see the title and her home university. So Sonja, please start with your talk.
Okay, good. So I mean, how should I say? This is a very broad conference, and so it was really difficult somehow to see about what I want to talk or what not. And I mean, then seeing that Eva wanted to talk about, let's say, symplectic geometry, contact geometry, and the interaction with dynamics, and maybe also some more physical systems, I thought I'd pick a topic where one at least understands what's going on, and where, when you then actually want to look for systems, you find also examples in physics and everywhere. So the idea here is a little bit that from a physical point of view, you say, oh yeah, I have an S1 symmetry. From a math point of view, you say, well, I work with an Hamiltonian S1 action. And Eva already said in the beginning of her talk that, I mean, there's this kind of nice systems which are called integrable, which technically consists of several symmetries. And I want to discuss or answer the question, when given an Hamiltonian S1 action on a compact four-dimensional manifold, when you can actually find another symmetry to turn the whole thing into a nice integrable system. So this is a little bit the idea of this talk. And as I said, one can find nice examples in physics. And when you look at the works of, for example, Holger Dullin or Holger Walkens, you also find, I think they did something with the hydrogen atom. So, I mean, there are definitely connections to, I mean, more materials, let's say. And I mean, Eva already gave some notation, and you see here that at least within symplectic geometry, usually, I mean, people sticking to M for the manifold and omega for the symplectic form. So this is also, I mean, my notation. And I mean, it also implies when you want to be non-degenerate that M is even dimensional. And as Eva already said, the standard example here is, I mean, well, R2n with coordinates Q and P, or Q1 to Qn, P1 to Pn. And I mean, this is, well, and coordinates the cotangent bundle when you want to see it like this. And as Eva already said, I mean, locally, when you're just symplectic and nothing else, it's quite boring because everything looks like that. So if you want to have locally something going on, you need to have something else, like, for example, a nice Hamiltonian system, because otherwise, I mean, there's nothing, no local invariance like curvature or anything like that, I mean, from the symplectic point of view. And for Hamiltonian systems, my convention is, I mean, I define the Hamiltonian vector field indirectly, but you can also then write it down in coordinates and have a look at the Hamiltonian equation. So I mean, here a priori, I mean, we're starting from something that is really, I mean, second bachelor, third bachelor, so a really honest ODE, and no operators, nothing here right now. And if you write it down then in the local coordinates, and I hope I didn't mess up the minuses, then you should end up with the Hamiltonian vector field consisting of the partial derivative with respect to P, or P1, Pn, and so on. And in the second half, then to minus the Q, or the Q1, the Qn. So it's some also referred to as the skew gradient. And so, I mean, then you can get also the Hamiltonian equations. So, I mean, we are here really in a classical situation, ODE, or more precisely, a system of ODEs. And I mean, at least in pure math, you always ask about classifications. And when you just look at the class of Hamiltonian systems, I mean, a priori, no chance to classify anything because, I mean, it can be anything. But in certain situations, when you put certain, how should I put it, conditions, you can find nice classifications. And so, for example, did Karshon in 1999 in dimension 4 on compact manifolds. There she could actually classify systems where the Hamiltonian flow is one periodic and where the action, I mean, is effective. So, I mean, technically, you just take the minimal period of that flow as for your action. And the interesting thing is that a priori one thinks, oh, well, I mean, Hamiltonian systems can be anything. And even if I just look at S1 actions, still it has lots of degrees of freedom and whatever. But funny enough, I mean, that stuff is discrete, is classified by some discrete quantities. So, I mean, she found that you can classify and effective Hamiltonian S1 action on the 4-dimensional compact manifold just by a few data. And here I just drew a couple of examples, and I mean, it's not on purpose that they are so symmetric. I mean, they can have more things, but I had some trouble with my, I should say, computer last week. More precisely, it crashed totally, and I had to do a complete reinstall, and so I only had a very basic drawing program. But I mean, let's have a look at what's actually going on here. I mean, these graphs, they have a couple of features. I mean, I have vertices, and they can have different types. I can have just points that correspond to fixed points of the action, or I can have fat points, and they actually correspond to fixed surfaces. So I mean, a whole bunch of fixed points next to each other. Moreover, what you notice is that here, I mean, some of these graphs, they seem to have edges, and these edges, they correspond to the stabilizers, or more precisely connect components of the stabilizers. And one usually then writes down there what kind of K here is actually stabilizing. I mean, the whole thing. And last not least, I mean, one could put here also the volume and the genus of the surfaces next to it, but I usually drop it because otherwise you have too many things on it. And let's just say for later on, I mean, there's a reason why you draw it like this, and like this means that technically in this direction here, I have the value of the momentum map, so of the actions of the Hamiltonian system. So let's say here is 0, here is 5, and so on. So for each picture. So I mean, here the projection down of the center of these points gives you where at which value of the in which level set, in which energy level it's happening. And so therefore, I mean, technically you can have energy levels where I don't have anything singular. You can have energy levels where I have, let's say, 2 things singular, or where I have a fixed surface, or here you actually hit a couple of stabilizers, but you can have much more variety. But as I said, I mean, I was a little bit limited in my drawing activities. If you look into Karshon's paper, she tells you exactly what kind of graphs actually can show up. Okay, and now, how should I say, this was a really nice class of Hamiltonian systems. And the main point is now to, if I have a system, to extend it with more additional, let's say, symmetries. And for that, I mean, I'm now aiming towards Liouville integrability, so the standard classical integrability for Hamiltonian systems. I mean, this is motivated by the energy conservation of Hamiltonian systems. And this means simply that when I really draw here a Hamiltonian system, and I look here at the level sets, then I notice that the solutions have to stay within the level sets. And the technicals, they have to stay within this energy level. And this is then usually referred to as energy conservation. And this means, I mean, from a geometrical point of view, that solutions, they have to stay within a lower dimensional set within the manifold. So you lose degrees of freedom where you can run around with the solution. And this is, of course, very nice because you have control. And if you are in dimension 2, I mean, 2-dimensional manifold with a Hamiltonian, technically, I mean, you almost know the system once you have the level sets, because, I mean, solution is 1-dimensional or just a point, and level sets are, well, usually 1-dimensional, except if the thing is somewhat flat. And then you know where the solution have to run around up to parameterization. And so the question is if one can extend these concepts also to, let's say, to imprison the solutions in even smaller level sets. And this is now what I'm aiming for. This is Liouville integrability. And this is also what I think Eva meant at the beginning of her talk with when one has an integrable system. And Eva was later aiming at Floer theory, where I said you want to, where you technically want to have a result about an autonomous system, but you need to perturb. So, I mean, she's leaving then the integrability, and for integrable stuff, I mean, the super symmetric systems there, Floer theory doesn't work well because, well, it's too symmetric and you don't get genericity for the analysis you need. But this is precisely what I'm aiming now here for. So I'm asking technically, I mean, how nice can a system be? How many symmetries can it have? Or what actually would be the idea to find symmetries? And so for Liouville integrability, I mean, you have a function, and then you look for more functions such that you have this kind of energy conservation with respect to each other. So you want that the solution of the one thing also do not just stay, which they automatically do, in their own level sets, but also in the level sets of the others. And I mean, if you have this, they stay in the intersection of the level sets, and then this means you drop in dimension. And then there is, I mean, I'm not going to talk about it, but there's the so-called Arnold-Liouville theorem, which actually tells you how much you can drop down with independent function integrals. I mean, which means you can get down to half of the dimension of the manifold, technically. Okay, and then comes the question, how do you express this in a more algebraic way? And then you finally notice that this is actually the notion of the Lie bracket. So when you just have a look at one function along another solution, and you look at the derivative of that, I mean, by plugging in the definition of the Hamiltonian vector field and so on, you find both Hamiltonian vector fields plugged into symplectic form. And this is usually the standard Poisson bracket then in classical symplectic geometry. Okay, and I mean, staying within each other's level sets means then that the Poisson brackets have to vanish. And with that, we are now ready just to define integrable systems in a classical way. And here for the rest of the talk, I am sticking to dimension 4 because the aim in the end is that I want to extend in this one action to an integrable system. And so I don't want to confuse you with lots of other notations. So we are now dimension 4. This means that given a function L, I only need the second one, or given the H, I only need the L. So technically, we have a function phi given by two components, L and H, going from M to R2. And this is the momentum map of a completely integral system if I want that the Hamiltonian vector fields are almost everywhere linearly independent, because otherwise, I mean, well, it's quite boring if everything is degenerate or too complicated, or it doesn't make sense. And on the other hand, I mean, I want to be integrable. So as I just explained, I mean, I want that the Poisson bracket vanishes. And this means in particular that I now can switch between the notions of being in geometry, like looking at flows, and working with algebra, so with actions. So when I just look at the flow parameters here, I mean, being an integral system means I have now two action on the manifold. And a nicer two action because it comes from the Hamiltonian momentum map. And this is now, I mean, a little bit the scheme, what I want to line out today. So, I mean, what we already saw is here down in the bottom right corner, the classification by Karshon in 1999. All Hamiltonian is one action, so I call it as one space because, I mean, with omega and this manifold and so on, they were classified. And what she managed to do was, here on the bottom left, given a couple of conditions here on the genus of the fixed surfaces and of the number of non-free orbits in the level set, so when I cut vertically through this graph, then she could actually lift it to a toric system. And she noticed that if I have a toric system and I project, I end up here. And I mean, this is certainly nice because, I mean, toric systems are the nicest and easiest case of integral systems you can find. So it technically means you have a system that has 2s1 symmetries. And a little bit later, I mean, well, I mean, there came then the question, I mean, can you do it more general? But the very moment you leave this nice toric world, it gets much more complicated. And the easiest of the more complicated systems I think of, and I mean, in dimension 2, you could consider was this class of so-called semitoric system defined by Pelayo and Van Gogh. And we're seeing later a little bit more about what it actually means and what it is. And then, I mean, this is the aim then of, or the end of the talk, when we actually get to the so-called hypersemitoric systems, which generalize these systems here, get as general as possible while being still reasonable. And then here in the lower, how should I say, line, you see that here, I mean, Karshon managed to lift and is one action under certain conditions to a toric system. Here, I mean, the first thing was the projection down, so recovering given such a thing. Here the underlying classification, and we found this here. Also HSS stands for Hohloch, Sabatini, and Sepe. And this is a work in progress, or more precisely, it's not yet really written up and on the archive. This is how you actually get up, then how you extend it. And then here, I mean, together with Joseph Palmer, we actually managed to lift all Hamiltonian S1 spaces. And so, I mean, the idea is to explain a little bit of this concept and the flavor of these systems here. And for all these systems in particular here and there, I mean, there you can put in, I mean, most of the nice physical systems. So so I think it's let's say this lifting question here is a quite natural question actually, and the space we found here is also a very natural one. And so let's maybe start here then on this side with explaining what's actually going on. Okay, I mean, when you think back to the graphs by Karshon, the main ingredients were the fixed points, or the whole bunch of fixed points, so the fixed surfaces, plus connection between them in form of the stabilizers. And so, of course, comes the question, I mean, first of all, what is a singular point? And in this situation here, going from dimension 4 to dimension 2, the definition is simply that the rank of the differential is smaller than 2. So it can be 0, this means a fixed point, or can be 1, so then I still have something moving, but it's not fixed. And another important notion is, whenever you work with singularities, you want to know how bad they can be. And the best case is always when you find some notion of non-degenerateness, because this usually means that you have some control, which means you have some, or which is defined as having a useful local normal form. And here in this setting, I mean, whenever you work with integrable systems and actions, you can come from the, let's say, algebra side, or you can come from geometry or whatever. And originally people worked here, I mean, the people who worked here, they came from, I think, mainly Lie theory, and they defined being non-degenerate via Cartan subalgebras, which is an abstract concept which works under certain circumstances quite well, but the very moment you have an explicit example and you want to know if the thing is actually a non-degenerate or not, it doesn't help you much. And there's the really nice thing that you can reformulate this complicated Lie theory, whatever condition, in linear algebra. So you need the Hessians to be linear independent, and you need to find a linear combination here of the inverse of the matrix of the symplectic form times the Hessian, blah, 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 such that we have 4 distinct eigenvalues. So, I mean, these notions are really something you can calculate. I mean, you can get your hands on it. And if the examples are nice, then it's not too difficult. And as I said, being non-degenerate means you have local normal forms. And there's a theorem which, I mean, I'm only mentioning here 2 or 3 names, but it has a longer history of how it was built up. And this technique tells you, once I have a non-degenerate singular point, that thing actually comes or decomposed into components. So I can have hyperbolic components or elliptic components or focus-focus components, which actually eats up immediately 2 integrals, or have a regular component, so something which is technically not singular. And with that, I mean, as long as I'm non-degenerate, I cover everything. The problem is, of course, what's happening if I'm non-degenerate, but I'm coming to that at the very end of my talk. And so, I mean, as I just said already, I mean, when we want to do these classification games, I mean, the first thing you start with are toric systems. And toric systems, if you consider from a group action point of view, you have 2 S1 actions that commute. And I bet everybody already saw at some point the rotations on CP2. I mean, here's just the map that gives it. And I mean, when you actually then draw it, I mean, so coming from CP2 down to R2, you notice that, I mean, here CP2, the image of that thing is technically just a triangle. And the singular points, I mean, here above the lowest strata in the image, I mean, here you have the elliptic points sitting over the vertices. over the edges, you have some elliptic regular stuff, and here in the middle, your non-degenerate, your not singular, there you have tori. And I mean, this again, this is Arnold Liouville that tells you that here, I mean, over non-degenerate stuff, you have n tori, so in this case, 2 tori. And the classification of toric systems was done by Delzant in 1988, and it is really super nice because it just tells you, I mean, it's classifying up to equivariant symplectic morphisms, but given a manifold, symplectic manifold with a torus action and a momentum map, you just evaluate the momentum map, and whatever you get here is a polytope. So I mean, having the image of CP2 in the previous slide being a triangle is not a fluke. This is always happening if you have, or that you get some polytopes is always happening when you have toric systems. And I mean, they cannot be totally arbitrary polytopes. They need to satisfy certain conditions. But this also means that, I mean, it's super nice. It's super practical because toric systems therefore are classified by a finite set of data. You can do it by combinatorics, but it's of course super special. And I mean, let's face it, how many systems are toric? I mean, there aren't that many. So the main point is then that here at least, I mean, just seeing once again the slide, we now know what the toric systems are, and under certain conditions, Karshon managed to lift, and when she projected, she also found these conditions back. So let's now be a little bit more, how should I say, practical and admit more systems, also from physics. And these are the so-called semitoric systems I'm now aiming for. Again, we're on a 4-dimensional manifold. And this definition goes back, I think, very originally to Van Gogh, somewhere around 2003, 2004, whatever. But since, I mean, the classification was done then by those two together, I usually just mention it both together for these things. So, I mean, originally they wanted to have, or they said the semitoric system is an integrable system where, I mean, the function inducing the effective Hamiltonian S1 action should be proper because they don't require M here to be compact, and you need, when you want to do classification or anything, somewhere you need something compact. Otherwise, usually, I mean, you're lost. And moreover, they only want to have non-degenerate singularities of the whole system, such that we have this nice local normal form. And now comes quite some restriction. They do not want to have hyperbolic components in these non-degenerate singularities. Main reason was that they just didn't know what to do with them in the sense of they couldn't classify. They wanted to have a classification. They had an idea what to do without this. So, I mean, they said, well, okay, let's have a look at that and let's see how nice they are. If you compare it now to toric systems, one notice two things. First of all, we do not have an underlying S1 times S1 action. We have an S1 times R action. So still we have the S1 symmetry, but whatever else comes here is more general. And when we compare what kind of singularities we may have, we see that here we have elliptic and elliptic regular, like in the toric situation, but we gain another singularity, the so-called focus-focus one, which is very often also just drawn as a pinched torus. So I think I have a picture here. And so to get some idea of these systems, it's a little bit like being perturbed combinatoric in a certain way, because, I mean, we do not have a super nice polygon in the sense of straight edges, like for the Delzant situation, where just with the edge, with the fixed points and the vertices, you could regain the whole thing. But here it's somewhat curved. But nevertheless, you still can see, due to the local normal form, that here over the vertices you have elliptic singular points in the manifold setting, and here over the dimensional 1 strata, so the boundary of this image of the momentum map, you have elliptic regular stuff, so technically a circle. Usually here in the middle, you have tori as before, but you can have a finite number of isolated singular points, which are the so-called focus points here. And the fiber then somehow is very often drawn as some kind of pinched torus. So technically, this means that when you have here nearby an honest torus, you just take one of these, how should I say it, loops, and you pull them close. So I mean, in algebraic geometry, you rather would say you look at the vanishing circle, and I mean, what's happening once the thing really vanished. I mean, these type of singularities, they also show up in I think Lefschetz vibrations and so on. So it's a common type of singularity considered in I think also chaos theory and so on. So I mean, whenever you do these kind of things. And now comes the question. I mean, okay, here in the picture we are a little bit wiggly here at the boundary, and we have here a little bit of a new singularity. And how much does it give us compared to toric systems? And on the one hand, let's put it like that. I mean, before we generalize, let's see what we still have. And von Gogh in particular noticed that when you have this wiggly image of the momentum map of the semitoric system, and you have here some focus value, and let's say this direction here is the S1 action, or the momentum map of this one action. Here we have the Hamiltonian of the R action. Then he said, well, okay, let's just cut in down here, and let's take out the cut, also in the manifold. And then you end up with something that doesn't have anything non-toric. And that stuff he actually could straighten out. So I mean, technically he could come up from here and put action angle coordinates. And the cost of it is that you see the curvature, I mean, the singularity is causing by getting here a kink and a fake vertex in the boundary. But you still have a lot of toric stuff in these semitoric systems. But they could be classified. And this classification counts, first of all, I mean, how many of these focus singularities do you have? Then it characterizes locally, I mean, the fiber of these things. So, I mean, how fast does the thing expand or not? And this is done by means of a Taylor series. And this technically means that, I mean, I'm busy with something infinite. So we are definitely leaving the toric world where we have just a finite amount of data. We are going to the infinite, I mean, ingredients, and therefore the whole thing, it's a much larger class of objects. We still have some toric flavor because, I mean, we have some kind of generalized polygon, namely here this kind of straightening out thing where you have a couple of degrees of freedom, I mean, how you straighten it out. It is important to notice or to keep in mind where actually that focus value ends up here in the straighten out polygon, because that thing is actually an invariant. And there's a last thing which I do not really want to address here because we don't need it at all. It's something that tells you somehow how this local system here fits into the whole system. So how locally this thing compares to doing this kind of straightening out with action angle coordinates. And so technically, when you compare it to the Zon's classification, going from a polygon, you go up to 5 invariants. And this is still done for systems for semitoric systems with some, I think, let's say semitoric systems as they are defined. I didn't say that I only look at systems that only admit one pinch in a torus, but you could also have several pinches in a torus. And for that, I mean, there's an update of this classification done, I think, 2 or 3 years ago by Pelayo, Tang, and Palmer, and they also managed to include that. So, I mean, they are fully classified now. And for people from physics, I mean, the first example I think people usually think about is the coupled spin oscillator. So, I mean, where you just have here, I mean, you're on the sphere times R2. Here you have a vector rotating. Here you're just rotating in the plane. Then you project the vector down, and you compare the angle between those two things. So on the one hand, you have the S1 symmetry, and your second integral comes then here from, by this coupled rotation, having a preserved angle. And this is then here the so-called coupled spin oscillator, and you can see here, I mean, the image of the momentum map, and you see it's a curved open polygon. And here, I mean, you have an elliptic point, and here, I mean, is the focus value drawn. And I mean, here the L and the mu, they are just some constants with which you can scale. And the second example also, I mean, is the so-called coupled angular momenta, where you have now rotations on spheres. And I mean, from pure mass, this is interesting because it's a compact manifold. So you can again then think about relation to Karshon's classification. And here, I mean, this system was created by having the rotation here and having here again the preserved angles, and then doing some scaling by means of a parameter between those two, between rotation and the angle, which technically means that you can move that focus point here. So you can go from toric to something else. And in particular, this idea lets you, I mean, come up with systems that have more focus points, because if you want to count focus points in this classification, I mean, just counting one is a little bit boring. And this was done then in 2018, where together with Joseph Palmer, we managed to come up with a system that has, for certain parameter values here, two focus points. And I mean, here, I mean, it was the first attempt. We were messing around with 4 parameters, but I mean, you can clean it up a little bit and enter this 2 parameters as 1 and as 2. And if we now look at the image of the momentum map, so at polytopes, it looks like that. And I mean, I think this side here actually is what moving the parameter and the coupled angular momenta would mean. And we were in particular interested here in the whole diagonal of the thing. So because here you see you have two focus values. And I mean, then Joseph Palmer together with Johan Lefloch, they managed to do it coming from Hirzebruch surfaces. So here the interesting thing is that you can actually build globally semitoric systems compared to the local classification by Van Gogh, by Pelayo and Van Gogh, who were just patching stuff together, which is not really practical when you really want to deform systems.
One question,
Yep.
Sonja. In your previous slide, when you say that it comes from the Hirzebruch, do they do this kind of nodal traits to put the singularities inside from the first picture?
Yeah.
How does the deformation work? Do they use the nodal traits of Symington, or they do a deformation, a different kind of deformation? Do you know this?
Let's go here to the system first. I mean, what's just happening here in this very original system was we started here with the coupled angular momenta, and we put a couple of parameters.
Yeah.
And then we changed the parameters, and we noticed there, oh, we get these things and we can observe it. And what Johan and Joy then managed to do here was they noticed that they came up with a more general approach to what to perturb.
Oh, okay, I see. For certain parameters, is Toric. Yep. Okay.
Yeah. So the first one was there's one action, and the second one they took some functions that were invariant under all these actions that show up, and with that, this function was quite determined. So you don't have much degrees of freedom. And with that, I mean, they just had a global function. They tried it, it worked.
Very
and
nice.
Then, and then they thought, oh, this is just a fluke. But now comes example number 5. It is not a fluke. That method, which they did with looking at the invariant functions on the reduced space, it works more general. I mean, because this was precisely what then the master student and I actually did with this octagon. So we started with an octagon. We considered the octagon as a toric system. And then we did the approach, what they did with invariant functions. So getting our perturbation via the invariant functions. And then we just perturbed, and that thing did what we wanted it. And really, I mean, here you have a one-to-one correspondence between the, let's say, combinatorics, so the picture you're drawing, and what the system is doing.
This is super nice because you're answering the second question. Like, you are putting here 4 focus singularities.
Yep.
But you cannot have 5. Your system produces an even number, no?
Yeah. I mean, what our aim was here, not just to get 4 different focus points, but actually to get them to collide and to get here then in the middle, when we're at t equals 1/2, to get fibers with 2 pinches. And it's even cooler because these fibers, I mean, you can write them down explicitly in coordinates. It's one line. You have the fiber, the formula for the fiber in one line.
That's very nice. So you have a correspondence between the let's say the invariance that you get having 4 pinch torus in 1 point and 2 pinch torus in 2 points. In a way, you have a deformation of invariance with your procedure. You are deforming the invariance somehow. It's very interesting.
Okay. Nice. Yeah. Let's see. I mean, later, I mean, in the question answer, whatever session, I mean, if you want, I can show you the precise construction. I mean, yes. I have later some slides as backup in case these questions comes. So
yeah, very nice.
Let's now maybe be quick because I think I'm also slightly running out of time. What we now actually are here in this whole story is this we already saw, the toric thing. We now actually explained what these semitoric systems are. And here, I mean, let's say what it corresponds to is not that much of relaxing. I mean, here, when you see the condition is, I mean, in both cases, that the fixed surface should have genus 0. And here they admit at most 2 non-free orbits. And here it's, I mean, at most 2 non-free non-fixed orbits. So technically, I mean, you don't want to walk through more than 2 of these edges in the graph, but everything else is admitted. But nevertheless, I mean, the very moment you have more than 2 edges, I mean, you cannot lift. And I mean, here I just put the authors once again. I mean, so this one here, the projection down is published. This was in 2015, I think, in the Journal of Discrete and Continuous Dynamical Systems. And this is still ongoing, or more precisely, not even yet on the archive, but we know how it works. And so now let's get to the last thing. I mean, to being able to lift everything. And there, I mean, the first thing you notice is you need to admit more singular points. You need to admit hyperbolic points in your system. But nevertheless, we wanted to keep the S1 action because otherwise, I mean, we are lifting as one action. So we want to lift it as one actions. And this is a little bit the reason why we called and the systems we ended up with hyper-semitoric systems, because we were coming from semitoric systems and we added something on the one hand more, so hyper, but on the other hand, we also added hyperbolic points, so hyper-semitoric system.
This is very nice. So you're assuming that you have your hyperbolic singularities, but you have this as one action everywhere. Yeah, that's the assumption. That's very cool.
Look, now it comes. We are on a 4-dimensional manifold. We assume here compact because we want to relate to Karshon's classification, which is done on compact manifolds. We have 2 integrals. The L again should induce an effect of the one action. So we have an underlying symmetry. And the other condition is just, I mean, all singularities of this whole system should be non-degenerate, except for maybe a finitely number of points that are degenerate, but they are super nicely degenerate because they're so-called parabolic points. So no mess going on. And with that, when you now look at what this class of system actually admits concerning what integrable system may admit is you can get all combinations of singularities, so elliptic, hyperbolic, focus for rank 0, so for the fixed points. You can have elliptic regular and hyperbolic-regular for rank 1. And the only thing that never ever can show up is hyperbolic, because the very moment you have an underlying S1 symmetry, that just cannot show up. I mean, you cannot have a hyperbolic point in the presence of an underlying S1 action. This is so, I mean, given an S1 action, the systems we admit are totally natural and don't have any kind of weird, whatever kind of restrictions on them. Okay, and now let's maybe have a look at how these systems look like from the point of view of the level sets and the fibers. So again, I mean, the image is some kind of wiggly polygon, but with some additional stuff. So I mean, they can have some kind of second layer coming out of it. So here, I mean, along this reddish line, this is the image of hyperbolic regular stuff, and there it bifurcates in the sense of that we have here a double cover. I mean, over this darker shape, I mean, in the middle, you have just, I mean, two tori disconnected. And here, I mean, over this hyperbolic stuff, you have, let's say, tori glued to themselves. And here at the very end, you see what kind of degenerate stuff may show up. And you can see it by seeing that you have some kind of torus, where here the upper one collapsed totally. And you get here, I mean, where it collapsed on the other one, some kind of teardrop shaped section, let's say. And this kind of phenomenon you can also get when you have, for example, something called a swallowtail, where you just, let's say, took one part here of your system and you pulled it in somehow, so over each other. So this.
So the hyperbolic singularities are not giving new invariants. Here.
What?
If you have an hyperbolic singularity in your hyper semitoric, which I would call super systems or something, because it's much better than semitoric. Like if you have an hyperbolic fiber, which corresponds to these two torus when they are regular, you don't get additional invariants down.
What
from the classification, from the semi-local classification that you have in a neighborhood, for instance, in a neighborhood of an hyperbolic, and now I'm not talking, I have to be very precise. Hyperbolic fiber.
I do not completely understand what you mean, but I only have, I think, 1 or 2 slides left. May I just finish the talk? We talk about it.
Sorry. Yeah.
Okay. Okay, then now, I mean, here comes the definition of a parabolic degenerate point. I don't have the time to explain it, but this is technically what it is. But practically, it simply means that, I mean, you just go down in the derivatives, and after being, how should I say, is a standard singular point that is non-degenerate, you just loosen up the next, let's say, derivative, give there a little bit of degeneracy or something that may vanish, and everything lower down again is nice and fine. So this is technically what this means. So this is really, I mean, from the point of view of being non-degenerate, the most non-degenerate degenerate stuff you can have. Let's just keep it like that and keep the picture of this teardrop torus maybe as a fiber. And so, I mean, the theorem is, I mean, it's on the archive, this paper, that when we're on a 4-dimensional compact manifold, then given any kind of Hamiltonian L that induces an effective S1 action, we can find a second Hamiltonian, so a second integral, such that those two things form a hypersymmetric system, meaning they commute and so on, and they don't have super weird singularities. And the interesting thing is that depending on how your S1 action looks like, it really may force you to have degenerate points in the image, so you cannot avoid that. But what you can do is you can somehow say what kind of degenerate points you want. And I mean, as far as I remember, somebody told me that Daniele Sepe and Sue Tolman are working on something with trading, I mean, something else for being much more degenerate. So, I mean, you have there some kind of freedom. But as I said, I mean, we opted for having the nicest type of degenerate points, and these are the so-called parabolic ones. And so therefore, from my point of view, I think these hypersymmetric systems are the nicest and easiest class of integrable systems to which you can lift an effective Hamiltonian S1 action. And I think when you start hunting in physics and chemistry and wherever for systems having this one action, I think you stand a good chance that they fall into this category. And here maybe just when you look briefly at how the proof would go, I mean, first, the idea is then to go back to be as toric as possible, to think of it a toric thing, then to create by so-called blow-up constructions and moving in nodal slides to create focus points. And then, I mean, this is, I mean, still was done together with Daniele Sepe, Silvia Sabatini, and Margaret Simonton, but it's not yet really on the archive. And then, I mean, the main trouble was that we couldn't at that time extend that thing actually to a full edge here in the graph. Also, I mean, you can have graphs with more edges. And this was then together with Joseph Palmer. And we relied on the fact that Holger Dullin and Alvaro Pelayo managed to plug to replace the focus point by one of these so-called flaps very, very locally. And then we managed to combine various techniques and just cut off here the edge. And that thing projects down then here to one of these edges. But I mean, I think I'm now really out of time. So let's just get to the overview of the results, that we have this one here. And so we can lift, but these things are not yet classified, apart from the thing that they are defined by these, by well, very natural properties, but not in the sense of, let's say, that this classification would be extended. So this is not yet done. And
yeah, this was my question precisely.
And with that, first of all, thank you everybody for your attention, and well, sorry for going over time.
Yeah, thanks a lot, Sonja, for your singularly nice talk. So discussion is